Okay, welcome to momentum. The big idea here is momentum is conserved for all collisions as long as external forces don't interfere. This is the part one of the notes. There will also be another video that will be part two. The concept of inertia was introduced and developed both in terms of objects at rest and objects in motion. Remember Newton's first law. In this chapter, we are concerned only with the concept of inertia in motion. So you have to have motion for momentum. A moving object can have a large momentum if it has a large mass, a high speed, or both, because it's the relationship that you have between mass and velocity. It is harder to stop a large truck than a small car when both are moving at the same speed. The truck has more momentum than the car. By momentum, we mean inertia in motion. Momentum is the mass of an object multiplied by its velocity. So momentum is mass times velocity. You'll see mv as mass and velocity, and we use a lowercase p to show momentum. A moving truck has more momentum than a car moving at the same speed because the truck has more mass. A fast car can have more momentum than a slow truck. A truck at rest has no momentum at all. A truck rolling down a hill has more momentum than a roller skate with the same speed. But if the truck is at rest and the roller skate moves, then the skate has more momentum. Can you think of a case where a roller skate and a truck would have the same momentum? So what would that be? That would be whenever the product of the skate in its velocity and the product of the truck in its velocity are both the same. So the roller skate and the truck can have the same momentum if the speed of the roller skate is much greater than the speed of the truck. For example, a 1,000 kilogram truck backing out of a driveway at 0.01 meters per second has the same momentum as a 1 kilogram skate going 10 meters per second. Both have momentums of 10 kilograms meters per second. What factors affect an object's momentum? So the two things that affect it are the mass of the object and how fast the object is traveling. All right, impulses. Impulse changes momentum. This is the big thing right here, that impulse changes momentum. The change in momentum depends on the force that acts on it and the length of time. So it depends on the force and the time. When you push the same force for twice the time, you impart twice the impulse and produce twice the change in momentum. The quantity force times the time interval is called impulse. That's what we're looking at. So impulse is force times time. The greater the impulse exerted on something, the greater will be the change in momentum. So don't just say impulse equals momentum. You have to say impulse equals change in momentum, because that's what it's doing. You're applying a force and you're changing the momentum. It's just not equal to momentum. Increasing momentum. To increase the momentum of an object, apply the greatest force possible for as long as possible. A golfer teeing off and a baseball player trying for a home run do both these things when they swing as hard as possible and follow through with their swing. Whenever you swing at a ball and you make contact with it, you don't stop swinging as soon as you make contact. You swing all the way through. You're trying to impart as much change and momentum as you can to the ball. The force of impact on a golf ball varies throughout the duration of the impact. The forces involved in impulses usually vary from instant to instant. A golf club that strikes a golf ball exerts zero force on the ball until it comes in contact with it. The force increases rapidly as the ball becomes distorted. The force diminishes as the ball comes up to speed and returns to its original shape. We can use the average force to supply for the impulse of an object. Now for decreasing momentum. If you were in a car that was out of control and had to choose between hitting a haystack or a concrete wall, you would choose the haystack. Physics helps you understand why hitting a soft object is entirely different from hitting a hard one. The change in momentum occurs over a long time. The force of the impact is small. The change in momentum occurs over a short time. The force of impact is large. You see this? You have a large force in a small time that it takes to stop. If you went back to the other one, you'll see that it's a small force and a large time to stop with the haystack. When hitting either the wall or the haystack and coming to a stop, the momentum decreased by the same impulse. The same impulse does not mean the same amount of force or the same amount of time. It means that the same product of force and time. To keep the force small, we extend the time. This is a very, very important concept. No matter whether you hit the haystack or the brick wall, you would get the same impulse. The final number that you multiply together, the force and time, would both be the same no matter which one. But here's where you want to know, do I want a large force in small time, or do I want a small force in a large time? When you extend the time, you reduce the force. A padded dashboard in a car is safer than a rigid metal one. Airbags save lives. To catch a fast-moving ball, extend your hand forward and move it backward after making contact with the ball. When you jump down to the ground, bend your knees when your feet makes contact with the ground to extend the time during which your momentum decreases. A wrestler thrown onto the floor extends his time of hitting the mat, spreading the impulse into a series of smaller ones as his foot, knee, hip, ribs, and shoulders successfully hit the mat. He just doesn't fall flat down on the mat, he kind of rolls onto the mat. The impulse provided by a boxer's jaw counteracts the momentum of the punch. A, the boxer moves away from the punch. Or B, the boxer moves towards the punch. Can you tell which one would be better? A glass dish is more likely to survive if it is dropped on a carpet rather than on a sidewalk. The carpet has more give. Since time is longer hitting the carpet than hitting the sidewalk, a smaller force results. The shorter time hitting the sidewalk results in a greater stopping force. We're going to do a lab in class that deals with this. The safety net used by circus acrobats is a good example of how to achieve the impulse needed for a safe landing. The safety net reduces the stopping force of a falling acrobat by substantially increasing the time interval of the contact. All right, when a dish falls, will the impulse be less if it lands on the carpet than if it lands on the floor? What do you think? Actually, it's going to be the same. No, the impulse would be the same for either surface because the same momentum change occurs. It is the force that is less for the impulse on the carpet because it's a greater time of momentum change. So remember, the same impulse will happen no matter what you drop it on. It's just how you get there. Do you want the large force or small force? If a boxer is able to make the contact 5 times longer by riding with the punch, how much will the force of the punch impact be reduced? Since the time of impact increases 5 times, the force impacted will be reduced 5 times. So this is a direct relationship. What factors affect how much an object's momentum changes? Force and time. All right, bouncing. This is a kind of a neat concept that you get to learn about here with momentum bouncing and how it either helps or hurts you. The impulse required to bring an object to stop and then to throw it back up again is greater than the impulse required merely to bring the object to a stop. Suppose you catch a falling pot with your hands. You provide an impulse to reduce its momentum to 0. If you throw the pot up again, you have provided an additional impulse. So as it goes down and you catch it, that's going to be 1 impulse. But then to throw it back up, you have to create a second impulse. So you've had 2 impulses act on it. If the flower pot falls from a shelf onto your head, you may be in trouble if it bounces from your head. You may be in serious trouble because the impulse is greater when an object bounces. The increased impulse is supplied by your head to the pot. So as it comes down and it hits your noggin and hits your head and bounces off, well, your head provided 1 impulse to stop the pot, but then your head provided a second impulse to bounce it off of your head, so you've had 2 impulses on your head. Cassie imparts a large impulse to the bricks in a short time and produces considerable force. Her hand bounces back, wielding as much as twice the impulse to the bricks. The block topples when the swinging dart bounces from it. Without the rubber head of the dart, it doesn't bounce when it hits the block and no toppling occurs. This is kind of a weird example to give. Water wheels used in gold mining operations during California's gold rush were not very effective. Lester E. Pelton designed a curved-shaped paddle that caused the incoming water to make a U-turn upon impact. The water bounced, increasing the impulse exerted on the water wheel, making it more efficient. It would spin faster because you're getting multiple impulses. The curved blades of the Pelton wheel caused water to bounce and make a U-turn, producing a large impulse that turns the wheel. So here's some pictures of that. How does the impulse of a bounce compare to stopping only? Once you bounce, you're going to end up with two impulses, not just one.